Welcome back to the channel, everyone. Today we'll discuss a problem from magnetism, and it's a quite interesting problem. And I have taken this problem from Supernova physics book, although I have seen to come this problem repeatedly in many institutes test. So it's a very standard problem now, I guess. Let's proceed. First, read out the problem once. A charged particle enters a region in which there is a frictional force proportional to the particle's speed, and the particle stops 10 cm from its entry point. Here it is shown in the figure that when b is equals to 0, obviously the particle will follow a straight line path, and due to some frictional force it will eventually stop after a certain distance. If the particle repeats its motion when a homogeneous magnetic field perpendicular to the plane of its trajectory is also present, then the particle comes to rest 6 cm from its entry point. It is also shown that when there is some B magnetic field, then obviously the particle will not follow a straight path, rather it will follow some spiral path. Obviously the spiral will also shrink or expand according to the nature. Obviously, since the velocity is decreasing, it will obviously shrink, and after a certain point it will stop completely. And in one case the magnetic field is B, and in another case the magnetic field is 2B. So in first case we are given when the magnetic field is B, it is 6 centimeter. I mean the displacement is 6 centimeter from the entry point, and when there was no magnetic field, displacement was 10 centimeter. And we are supposed to find the displacement of the particle when there is a net magnetic field of 2B. So I'm moving to the solution part. The frictional force I have assumed as minus k times v. Obviously k is some positive constant, and it was mentioned that it would be opposite to velocity, so I have put a minus sign here. So first calculate when the magnetic field is 0, I mean no magnetic field. That will be a very simple case because there will be only one force, that is the frictional drag. And obviously in each case I have assumed the particle is entering the region with a speed of v0. And acceleration in this case will be minus of k by m times v. Obviously if you divide force by mass, you will get the acceleration. And acceleration you can write as v dv ds. So now there will be cancellation of v from both the sides, and if you take ds to the right side and integrate the both sides, what will be the limits? Now initially the velocity was v0 and displacement was obviously 0 because we are calculating displacement from the entry point, and finally the displacement is s0, I have assumed, and as it has stopped finally, so we'll claim the velocity as 0. So there will be actually minus v0 and from left hand side after integrating, and there will be a minus sign on right hand side as well, so I have cancelled both and directly written v0 as k by m times s0. And now taking only the magnitude, we will erase the bar from both the sides. So from vector 2 we have shifted a scalar equation, that is s0 equals to mv0 upon k, and this is given as 10 centimeter. So it's the basic part, and I hope it's clear. Now the more interesting part is when there is a magnetic field. So if there is a magnetic field, there will be another force of magnetic force, that will be q times v cross b, and frictional force will obviously be there here also. So net force will be the superposition of magnetic force and frictional force. So this is the net force, and net force I have written as mass times acceleration as m dv dt. Now you just take the dt to the right hand side. Left hand side will be m times dv, and after taking dt to right hand side, this will be obviously very simple, that k times v dt, there will be a minus sign as well. And when you are multiplying dt with this term, I mean q v cross b, as b is constant, I mean uniform, that's why I'm claiming that whatever be the integral value of v bar dt, will cross product that with b and will get the same result. I mean, let me erase here and write here. I am claiming that v cross b dt, this integral value is same as that of v dt cross b. This is my claim, right? This is the idea, because b is uniform and b is all, and another point is b is always perpendicular to v, right? So now what is v dt? V is actually ds times dt, where s is the displacement, obviously. So v dt is nothing but ds. So I've written ds here. So the limits will be the limit of displacement from initial condition to final condition. So what will be the limits of ds? Initially it was 0 and finally s1 as per our assumption. I have assumed in this case the displacement is s1. And obviously initial velocity was v0 and finally it has stopped, velocity is 0. So this will be the equation after integrating. Now again the interesting part is how we will proceed from this vector equation to a scalar one, right? Because we will deal with speed and magnitude of displacement. So that's our motive. So we are not interested in vector equation, rather the scalar equation will be more helpful. So we'll take modulus from both the sides. Taking modulus from left side, we will end up getting mv0, and the interesting is the right hand side. So q times s1 cross b. S1 is, if I am say that the motion is happening in the plane of this screen, so S1 will obviously be in the screen of this plane and B was perpendicular to the plane. So what will be the direction of B cross S1? Is it will obviously be perpendicular to both B and S1. Let's say this is the direction of B cross S1 or S1 cross B. Obviously both are not same. I am not claiming that S1 cross B. Let me wait. Let me be accurate only. Wait. Yeah. Let's say this one is S1 and this is B vector. So S1 cross B will be in this direction. It will be S1 cross B. And this will be the direction of minus S1. So if we multiply a scalar k with this, it will just change its magnitude, not the direction. So this is the direction of minus of ks1 and this is the direction of s1 cross b, right? So you can clearly see that s1 cross b and ks1, these two vectors are perpendicular to each other. That means this is one vector, let's say this is a vector, and this is one vector, let's say b vector. These two vectors are perpendicular to each other. So what will be the magnitude? When we'll add or subtract these two vectors, we'll write square root of magnitude of a square, that is its magnitude will be, let me write it here, square root of a square plus b square, if this is the a vector and this is b vector. So b vector magnitude is very clear, it is k times s1, but a vector magnitude, what will be the magnitude of a vector? It will be again the magnitude of cross product of two vectors. So a vector magnitude is, q is obviously a scalar, s1 cross b. Now you can clearly see that s1 and b are again perpendicular. So s1 cross b will be nothing but magnitude of s1 times magnitude of b. This is the magnitude of s1 cross b, because it will be s1 b sine theta, no, and sine theta is 90 degree for this case, so sine 90 degree is 1. So s1 cross b's magnitude is s1 times b only. So that was one critical part. I hope it's clear. If it's not clear, you can go back and listen to this part again. So let me erase a few things, otherwise it is looking very clumsy. So wait, yeah, a b, yeah. So this one was the part I was trying to explain to you, that how after taking modulus to both the sides, from this step to this step I have come, right? So if it is clear, now the problem is almost done, I guess. Now you just square. Okay, have I done some mistake? Wait. No, it's fine, I guess, yeah. So if you take s common from here, I mean s1 square, after the in outside the square root there will be one s1. So s1 will be mv, and the rest of the terms you put it on the side of mv naught. You will get s1 as mv naught upon root under k square plus q square b square, and just divide the numerator and denominator by k. You will get mv naught upon k by root over 1 plus qb upon k whole square, and mv naught upon k was our s naught, right? Let me show it here. Yeah, mv naught upon k was s naught. So s1 is s naught upon root over 1 plus qb by k square, and this is 6 centimeter as given, and s naught was also given as 10 centimeter. So we'll put it here and we'll try to calculate qb by k term, because in case of S2, where S2 I have assumed for the case when magnitude of magnetic field is 2b, everything will be same of this calculation, only the magnitude of magnetic field has been doubled. So in expression of S1 we will just replace b with 2b and we will get the expression for S2. So this is our expression for S2, right? So only if we can calculate the qb by k term, we will be done with the solution, because s naught is again 10 centimeter given. So from here I am trying to calculate that only. So now it's simple calculation, I guess. Now square the both the sides and take 1 plus qb by k square term here, and it will be 25 upon 9. So qb by k square will be 16 upon 9, and multiply both the sides with 4. You'll get 2 qb upon k square, 64 by 9. Just put this value here and you will get this. After calculating, the answer is coming 3.51 centimeter. So the major catch, I would say, that when the both magnetic force and frictional force is there, how you will calculate the displacement. Even if you come at this step, I mean the vector equation, the modulus, after taking the modulus, the solution to a scalar equation was a bit tricky, I would say. So if you can crack that part, I hope the problem will be very easy for you. Yeah. So thank you, and that's all for today. We'll see you very soon in next video with some more interesting problem.